Hello, everyone. Thank you for joining us today. In today's workshop, we will learn how to manipulate and clear data. As you know, the most important tool in a data scientist job is having a good and clean data set. And in reality, oftentimes the data come from different sources and it's not immediately ready for any analysis. So in today's session, we will learn about all the tools, processes, and strategies that a data scientist can use in preparing their data sets. And with us today is Brian, and he's going to take us through this journey. Thank you, Brian, for joining us. And I'm handing over to you very quickly because we have lots to cover.
Yes, thank you. All right. I am just switching over to my screen. Welcome very much. Thank you for joining us this morning. I apologize. It is 4 o'clock in the morning where I am in Northern California, so if I seem a little groggy, that's why. But I'm glad to be here with you here today. Um, so we are going to be going over some of the techniques that go into the working with data kind of before you're trying to visualize it or do anything with it from a machine learning perspective. Generally, you want to read it in, you want to play around with it. And in the process, you may notice that there are missing values, and that complicates how you end up getting insight into what's going on with those values. Um, if you have, not a number and you try to add a couple of other things together in with that, you end up with bad results. So it's important to make sure that we've got the data sets clean before we go and try to do anything with it. So we're going to look at some techniques that go into that are provided by Pandas and NumPy and the various tools in this technology stack that we're using. We are not going to cover the absolute basics of going through Jupyter notebooks and things, but in the chat room, we're going to share with you a link to the repository. And if you wanted to follow along, you can go ahead and go to github.com/Microsoft/reactors, as I'm showing here, and clone the repository. That will get you quite a lot. There's several things that are going on there. Um, but I just wanted to show you where in the repository we are going to be focusing. We're going to be working in the workshop resources, data science and machine learning, data science 2, workshop materials, and then the first Jupyter notebook there is called 1 Cleaning and Manipulating Reference.ipnyb. So if you grab this repository and clone it, and then head down to workshop resources, data science and machine learning, data science 2, workshop materials, you can find the Python notebook and some of the data sets that we're going to be looking at there. Now, once you have that available, if you've got Visual Code installed with the Python extension, then the cool thing is you can just run these Jupyter notebooks directly in Visual Code. So you can stick with, if you use it as your development environment, you can stick with it and benefit from everything that it has to offer in terms of the code completion and things like that. So in any case, that's where I am. I've read in the Jupyter notebook from the repository that I just showed you, and we now have this this set of exercises for manipulating and cleaning the data. So generally, the data that you have to manipulate, we're going to want to get into some form that allows us to easily select columns and rows or specific subrows, rows with certain values. And that's one of the things that the Pandas data frame does for us. So if any of these concepts are new to you, I encourage you to go back and maybe visit some of the other workshops and go through the notebooks to get you comfortable with them. But the basic structure is Python is the programming language that we're using here. It provides good functionality for general purpose programming, but it's not particularly well suited on its own for high performance numerics. So NumPy basically helps solve that problem by giving us a homogeneous in-memory, high-performance way of representing potentially very large arrays of data sets. And then Pandas builds on top of NumPy to give us the data frame capabilities. And so the data frame is really like a programmatic spreadsheet that you can interact with and get the columns and sort the rows and everything. And if you've ever done anything with R has data frames, and if you've ever done anything with Spark, the Spark environment with Python or Scala, there are data frames there as well. So in this first section, we're just going to explore some of the work with the data frames. And so we're going to, in our first cell, import pandas as PD and scikit-learn datasets. There's a method called load iris, which loads in a very famous dataset from the early 1900s about iris flowers. And it's a very common dataset to introduce people to machine learning to, because it's a fairly clean dataset, and you can do some interesting things with it, like build a classifier. So based on the characteristics of the flowers, you could maybe try to predict what a new flower might be compared to the ones that you've seen. So we're going to import pandas. We're going to pull in the load iris functionality, and that's going to give us something called a scikit-learn bunch, which is not a data frame. But in the scikit-learn bunch, there is a key called data, and that gives us our rows and columns of data. And there's also a features name key in the scikit-learn bunch. So we're going to set the columns to be the names of the features and the data to be from the read-in data itself. So at this point, we've read it in, but we don't know really what it looks like. And one of the things that the data frame can tell us is a little bit of information about each of the columns. So if we call iris dataframe.info, then we see that there is a 4 columns, and each column is associated with a particular feature or attribute of the flowers. We have the sepal length in centimeters, the sepal width in centimeters, the petal length in centimeters, and the petal width in centimeters. So if you're not a biologist, petals and sepals are just part of the structure of the iris flowers. If you do a Google on iris, you'll see the different parts of the flowers. So we have 4 columns, and each column has 150 rows. So we have 150 samples, and the data type, you can see, has been kept to floating point 64 numbers. So Pandas is able to represent this homogeneous, clean data set with floating point numbers, and it is able to store it down in the C level as opposed to up in the Python level. So it's compiled, it'll be faster than interpreted, like Python math often is. So this gives us an overall sense of the structure of our data, but we'd like to see some of it, right? So the next thing that we can do is to call the head function on the data frame. And as you might imagine, that shows us the head or the top several rows. By default, we have 5 columns shown, and we see that we have, 5 rows shown of the 4 columns. So we can see the first row has a sepal length of 5.1 centimeters, etc. You may want to see more of the data for whatever reason, and fortunately, the head function gives us the ability to do that. But if you're following along, or when you're going through this later, if you're watching the video and following along, then it'll be useful for you to type in some of the exercises as well. I'll show you some of them, but these are intended for you to do a little bit of exploration. So in Python, if you have a variable and it has methods and you want to know more about it, you can run the name of the method with a question mark after it, and the documentation for the function will come out. There's a question, does the GitHub link contain the Jupyter notebook? Yes. So if you go to Microsoft Reactors at GitHub, and then navigate down through workshop resources, data science and machine learning, data science 2, workshop materials, you should be able to find the Jupyter notebook that we're going to focus on, called One Cleaning and Manipulating Reference. So if you have VS Code installed with the Python extension, you can just open up the notebook directly in code. All right, so the exercise here was to say, how do I figure out how to show more than the default 5 columns? And we can see that the documentation says there is an n of a parameter called n, which is the number of rows to show, and by default it's set to 5. So in the end, if you want to see maybe 10 rows instead of 5, you can just pass that in. It's the default. It's the first column, the first parameter. Therefore, it will accept it as the value. So n equals 10 shows us the first 10. All right. Now, this is based on the default sort order, and you may want to look at the last couple of rows to see how far down the values go if they were sorted in some kind of way that a one column was driving it. So in that case, there's the tail function that is not going to surprise you. By default, shows you the last 5. And as you know, you can pass in a variable to head. You can also pass in that same variable to tail. And in the end, you'll see however many rows you asked it to show you. All right, so this is just us getting comfortable with the data. We've read it in. We've seen the structure. Also included in the scikit-learn bunch that we read in is the category of each of the flowers. So that tells us the first 50 are setosas, the second 50 are versicolors, and the final 50 are virginicas. We're not actually going to be doing that part of the machine learning now, but generally that's what we would do for supervised learning. We would try to build some kind of classifier to say, okay, well, given this genetic variation in the features, how does that correlate with the output classifier labels, and then try to be able to make predictions. So that's what we do with the iris data set. But as you'll see momentarily, we can create our own data frames. You can read in data frames from spreadsheets. So if you have comma separated values or Excel spreadsheets or things like that, those are very naturally already in the column and row order. So those can be read into as a data frame. Pandas also has the ability to issue SQL queries against a SQL database with the right kind of connector. And so the result sets of the queries can also be made into Pandas data frames. So there's lots of different ways that we can come across this data. And if you are pulling things together from multiple sources, there's a very good chance that some of the data from one source might have some values that are missing. And once we start trying to connect the data up, that missing data will potentially be problematic with what we're doing. So the goal next is to use Pandas to find where there are missing values, just so we don't accidentally try to do something and draw inappropriate conclusions, right? Because the analysis of bad data is bad analysis generally. So missing data is represented in a couple of different ways. Python itself has an object called none, and that's really sort of like a placeholder for missing values. You can think of it kind of like a null, except it isn't actually an object. So it isn't a null reference, but it serves the purpose of a null in, say, a language like Java. But mathematically, the IEEE, the Institute of Electrical Engineering, that defines the floating point standards, also has a mathematical way of representing not a number. So something that is not a number has a specific representation, and that's useful for math problems that, you know, if you divide by 0 or something, right, that causes things that aren't valid numerical results, therefore they need to represent that somehow. But Python and Pandas and NumPy use not a number or non as a way of representing missing results in the data sets. So what we want to do is we want to come up with some tools for finding these things, because if you have thousands and thousands of rows, it's going to be hard to notice that. There was a question about whether the video will be available, and yes, you should be getting, you should be able to get to the video later. So we need some programmatic tools to help us find the missing results, and so that's what I want to focus on in this section. So we're going to import NumPy as NP. We're going to create a NumPy n-dimensional array, and we're going to pass in a Python list with the numbers 2, the value none, and then 6 and 8. So obviously, this is not something you would want to do by hand normally. We're creating some data with missing values just to show you what it looks like, and we're doing so on a small scale just so it's easy to see. But these same tools will help you with larger data sets as well. So we're going to execute the cell, and the first line here assigns to the variable. The second line here is the value of the variable, and that becomes the value of executing the cell. We see that we end up with an array, and we have our numbers in it. We have none in it, so it's accommodated the none, but it's also done something interesting. If you recall back up here, right, when we were looking at the iris data set, we had numeric values for the data type for the columns. That's because this is a very clean data set, and we didn't have any missing results. Therefore, the shape that it was in could be treated homogeneously as floating point numbers. But down here, when we mix in this case intentionally, other cases it won't be intentional, you mix in numbers and nones, then we have to put this in a homogeneous form to work with NumPy. So it has to change the data type from being integers for the 2, the 6, and the 8 into more generic objects to accommodate the fact that there's a none in there. So this is where this could have performance implications beyond the mathematical portion, and that's a conversion that we want to try to avoid. So there's a question, how can I deal with missing data? That's what I'm about to show you. So we'll help you with that in just a minute. Okay, so now that we have our data read in, this is not a data frame yet. This is still just an n-dimensional array in NumPy. Pandas builds on the NumPy arrays. But now that it's been converted into this format, we notice that we still have a problem in that if we try to sum up the values, we have 2 plus 6 plus 8. That makes sense, right? That's 16. But 2 plus none isn't defined, right? There's no meaning to the concatenation or the arithmetic addition of an integer and the none type. So we can see that it's actually considered an error by Python, and the Jupyter Notebook tells us that. So if you're trying to do math, if you're trying to summarize or sum up or take the average value of the columns, and you do have not a numbers or nones in there, that can often cause problems. And the reason for that is just mathematically, and in its implementation, NumPy is not a number, and none as well are not defined for arithmetic with integers, so the answer is always not a number. So not a number plus 1 is not a number. Not a number times 0 is not a number. So normally we think anything times 0 is 0, but that's only if you're dealing within the space of the defined value space for the operations. So addition is not really meaningful when you're involving things that aren't numbers. So that's what NumPy is telling us. All right. Now, there are elements, some of the NumPy operators do handle the missing values, so it doesn't throw an error like we saw above, but it's not very helpful, right? So if we have, in this case, 2, not a number, 6 and 8, if we try to sum them up, take the minimum value or the maximum value, again, it doesn't throw an error, but it returns not a number. In case you're wondering what's going on here, if this is not something you're familiar with, once we set up the NumPy array, we're evaluating sum, min, and max individually. But when we join them with commas like this, that creates a tuple, and the tuple is just sort of a lightweight way of storing a couple of values. Oftentimes in Python, you'll see return values that want to return more than one value from a function. We'll group them together like this in a tuple. So just the 3 values separated by commas here generates a Python structure called a tuple. That's why it's in parentheses there. All right, so now for if you're following along, either now or later, the next exercise is what happens if you add np.non and none together. The question really is, how's it going to behave? Is it going to throw an error, or is it going to simply envelop the results and return not a number? So if you try it out, we say np.non plus none. Try to guess, think about what it might be. And when we run it, we'll see that we're back to operations with plus addition are not defined for none, so we don't get the non-handling that we saw with the aggregates. Those are handled behind the scenes in a way that keeps the flow from throwing exceptions. But in this case, generally, we do not want to do addition or arithmetic in general with either of these values. Now, keep also in mind that not a number is only defined for floating point numbers, and that's because it's an IEEE specification. There is no equivalent for not a number for integers, strings, or booleans, which is why if we need to represent those as missing values, the none type from Python is a reasonable way of doing that. But the real performance benefit that we get from using NumPy is in the fact that the data is homogeneous and able to use compiled forms of things, of the math, the U functions that are also operating in a precompiled way. So if we do mix in the none type, as we see, that elevates the data type of our arrays and things back to objects instead of numbers, which again has implications on performance. So this is just explaining why we need to deal with this. Now, in Pandas, we have the ability to look for those and to drop them, to replace them with other values. So this next section is going to help us explore what that looks like with respect to working with the Pandas data structures. Now, the first Pandas object type that we're going to use here is called a series. And a series is really just kind of an indexed collection of values. So in this case, I'm going to default to creating a series from a Python list, and I'm going to tell it I want it to keep the data type to be an integer. And so if I run that, you'll see that we end up with something that looks like this. Now, this kind of looks like we have 2 columns, but we don't. We have 1 column, and the values of that column are 1, 2, and 3. But we also have an index. And so when you don't specify an index, Python will, or Pandas will default to a positional index. So row 0 is the value 1, row 1 is the value 2, etc. So if I wanted to interrogate, let me add a cell here. If I wanted to interrogate the value of, say, int series 0, the answer is 1. If I want to interrogate the value of 2, we'll see that it's 3. Now, also keep in mind, we start counting with 0 in Python. So the first one is 0, the second one is 1. That's very easy for people to get an off by 1 error when they're thinking about this, but that's what's going on. It's also possible to find ranges of values. So if I wanted to select the first and second rows, that's going to show me the values 1 and 2. The range of values is interpreted there as the keys. You can also just say, I want all the values, right? And it's going to show us 1 through 3. All right. Now, once you have your data set, obviously the goal is to remove the missing values, but for our purposes, we want to put it into a state where there are missing values. And just to show you, one of the things you can do is you can assign one of those values to be the value none. So if I say int series, say 1 equals none, and then look at the int series, you notice that that has been interpreted as not a number in the Pandas series because we want to try to keep it homogeneous. None doesn't really mean anything specific, so it's okay for it to deal with that. But notice it's also then changed the data type to floating point numbers, whereas originally it had been integers. So because there is no integer representation of that, and we do want to keep the data homogeneous, it promotes it to a floating point number and substitutes the non for the none. Again, this is just showing you like the low-level mechanics. That's not something you would normally do. But now that we have a missing value in our series, we can call some of the functions that are available on the series to help us find them. So the first one is called isNull, and it generates a Boolean mask that tells you where there are missing results. And not null tells you where there are not missing results. So if I go back here and ask the int series to say int series dot is null, notice this gives us maybe not the results you were expecting. It's telling us false, true, and false. So this is saying 1 is not null, non is null, 3 is not null. And so that's returned that way. Notice if I call the not null function, it's just going to invert the results. 1 is not null, non is null, so that's false, and 3 is not null, so that's also then true. Now, the cool thing is, once you have that, you can use those masks to select the rows. So let's generate a new data set. We're going to mix in a 0, a non, an empty string, and a none. It sounds like the beginning of a joke, right? An integer, a non, and then a string walk into a bar. So when I run this series now has values in it. And Python does support this concept of truthiness, right? Where anything that's 0 is considered false and anything that's not 0 is considered true. That's not really what's going on here. Is_null is a deeper determination that says, is it a missing value? And so even though 0 would evaluate to false in Python, it is not a missing value. So when we run is_null on this series, we'll see that the answer is false, right? 0 is not missing, non is missing. An empty string also, right, doesn't convey any value, but it's still a string, right? So it's not a missing value, and so that's considered false. None is considered a missing value. So obviously it would be easy enough for us to see in a series with only 4 values, but these are useful when you have hundreds or thousands of rows to find them. So what happens if we take that not null response and we use that as the index to select from our series? So this is a 2-step process. The first one is going to evaluate to the not null Boolean mask that we saw before. Then we are going to select the values for which it is not null. So this is a convenient way of returning the 0 and the empty string. Again, this is an intentionally goofy setup just to show you some of the mechanics of dealing with these values. What happens if I select example 3 is null? Then that reverses the logic and then gives me only the values that are considered null. So we see that position 1 is considered a none, position 3 is considered a none. So we have the 4 values in there. Also keep in mind that selecting rows like this doesn't change anything. So if I turn around and try to print out the whole thing again, or whether the whole thing has null values, they're all still there. It's just that this is a view of the data set with those things filtered out, either the null ones or the not null ones, depending on which index you're using. So these are useful if you just want to be able to find where these results are. You can also ask, if you keep on calling functions on the results, you can say how many missing results are there, or are there any missing results, and they will sum up and give you those answers. So how can we handle empty string values if we're handling empty values based on a not null function? Hold that thought. I'm going to show you some ways of dealing with the missing values in just a moment. Okay, so to the question asker's point, how do we end up dealing with these things? Well, once we have a way of determining that they're missing, and Pandas has this is null, not null thing that we've just discussed, one of the things that you can do is to drop the missing results. Now, before I do that, before I run this one cell here, I just want to show you again what the results look like. So we have 0, none, empty string, none. If I say drop NA, it returns just the rows that have values. So we've dropped the missing values, but we are returning a series that has only the non-missing values in it. Notice it kept the original index, but also the reason that it did that is because all the data is still there. If I try to print that out again, we see it's still there. So drop NA, unless you tell it to do it in place on the object that you're invoking it on, doesn't modify the object that you're on. So that's what's going on here is we're saying, I want you to drop it, and then I want you to assign the result of that to the same variable. And at this point, we see the same result, but example 3 now only has the 2 rows in it because we dropped it and then we overwrote the full result set. So, I mean, you'll do that if you just don't care about the missing results and you want to get rid of them and not think about them anymore. There's no reason to keep them around, but otherwise you usually want to do the drops and see the impact before you actually assign it and blow away your original data set. Sometimes people will read it in like data raw equals, and here's the data frame, and then data clean equals data raw dot drop NA. So now I have 2 variables. One points to the original data set, one points to the clean data set. And that way, if I want to go back and do something with the original data set, it's still there for me. It's up to you. Depends on your personal choice. So in this case, we have told it to just drop the missing values and update the variable to not have them. And that looks exactly like if we had selected just the not null responses up above. All right, let's build a more complex data frame. So in this time, example 4, we're going to be having 3 columns and 3 rows. We can define that as a multi-dimensional array, basically here, right? We have an array of arrays, or a list of lists, And here, the first one will be interpreted as the first row. So upper left-hand corner will be 0, 0. The value will be 1. Row 0, column 1 will be np.non. Row 0, column 2 will be 7. So read it in. We can see that it looks exactly like the values there. But notice it has also promoted these columns to be floating point numbers again, even though they were integers originally, because we have to have homogeneous data in the underlying structures. Pandas is built on NumPy. NumPy is going to, by default, try to keep the data homogeneous like that. All right. So now I have the ability to select. So if I say example for 0, notice we're pulling out column 0. If I want to pull out column 2, I can pull that out. You'll see below how we can select rows or columns in just a moment. All right, so example 4. Let me remind you and show you the whole thing again. We have this row has 1 missing value, this row has no missing values, and this row has 1 missing value. If you say drop NA, by default, it's going to drop any row that has any missing values. So any at all, we now see that we no longer have row 0 or row 2. We're left with just row 1. That's the only row that did not have any missing values. And that may be the right thing to do, but depending on how much data you have, you may have just thrown away too much of your data. And it's possible that there's a different approach that you can take other than dropping the missing values, and we'll see that in just a moment. What if you wanted to drop the columns that had missing values? Well, by default, when you're dealing with data, right, the columns represent the features, the rows represent the samples or the observations. You don't necessarily want to drop the feature because that's what you're learning from, but the default behavior is to drop the rows that have missing values. If you want to drop columns that have missing values, then we have to tell it when we drop NA that we want to focus on columns, not rows. So rows are considered axis 0, columns are considered axis 1. If I say drop NA axis equals columns or axis equals 1, that means the same thing, you'll see that we end up with a single column because we've also dropped any columns that have any missing results. So why is the third column not a floating point and an integer? Because that column is stored as a series. Each column is its own series, and that column is complete and homogeneous. So it's more efficient to store it as its original form as a series of integers. The Pandas data frames itself isn't trying to homogenize the entire thing. It's trying to homogenize the columns. I apologize, I didn't mention that. That's a good observation. If I wanted to convert them all to floating point numbers, that's something that you could do as well. But by default, it only does it where it has to, and it only does it for the first 2 columns because of the missing values. All right, so drop NA doesn't change anything unless you assign it or tell it to do it in place. By default, it drops the missing rows that have any missing values in them. If we specify axis equals 1 or axis equals columns, then that allows us to change which part of the data we're dealing with. Now this is a little bit brutal, right? Again, one single missing value and the entire column is gone, or one single missing value and the entire row is gone. So we have some other ways of dealing with that. So for example, we have parameters called how and thresh. So how is indicating a strategy, thresh is indicating a threshold. So for example, if I assign a new value, just so we have some more variation in the data, we now have a third column that is all missing values, right? So when I say example for 3 equals np.none, that's going to repeat the value for that column over and over and over again. So we have a column that is entirely empty. We have one that's entirely full, and we have 2 that have 1 missing value. Row-wise, we have 2 missing values, 1 missing value, 2 missing values. The reason we did that is so that we can deal with the thresholds. I'm going to skip this exercise. You can do that yourself. Here I say, okay, I want to drop the row axis threshold equals 3. That says only drop any rows that have fewer than 3 values. Now, if I said threshold equals 2, I will pick up 3 of the columns, or 3 of the rows, because this has 2 values, this has 3 values, this has 2 values. So it's just a way of saying, look, I don't want to throw away all of my rows just because there's 1 missing value. If they still have at least this many columns, then keep them around. So this is up to you, right? All of these things are mechanisms. They're not policies. You're going to be the one who's going to decide the policy of what to do. The mechanisms are simply there so that you have some options. Under some circumstances, you might just want to get rid of a column that has all missing values, or a row with all missing values, or a row with some number of missing values. But how and thresholds give us that ability. So for example, if I say how equals all, let me go up here and say drop NA how equals all. By default, our axis is our row axis. We have no row that is all missing values, so no rows are dropped. So that's kind of like setting the the threshold to 1, right? If there's at least 1 value, we keep it around. If we say how equals any, you'll see that everything gets dropped because everything has at least 1 missing value. So that's how at work. If I wanted to drop the columns that are all missing values, then I need to specify the column axis, a how of all, and so now I kept the first 3 columns, but I skipped the last one because it's all missing values. All right. So the next step is to say, what if I don't want to drop things? What if I want to fill in the values with something? And so I'm going to rebuild a new series here. I'm going to have a custom index of A, B, C, and D. The implications of this are that I can now refer to example 5, sub A, and it will return the value 1. So in this case, A is a keyed index, not necessarily a positional index. Also keep in mind, as long as your index values are not don't have strings in them, or I'm sorry, spaces in them, you can use the dot notation you'll see a lot. So example 5 dot A is the same as example 5 of A as the key. So in this case, we have a 1, a none, a 2, a none, a 3. And if I want to fill in the null entries with a single value, such as 0, that's easy to do. The method fill NA, so fill in missing values, will do so. So notice we have now 1, 0, 2, 0, 3. Just like the drop NA, this hasn't changed the original data frame or the original series because we didn't assign it back to the same variable and didn't tell it to do it in place. So if I go back and look at it again, we'll still see 1 non, 2 non, 3. Think for a moment, what happens if you set everything to 0? Obviously it works, it's something we can do, but analytically that might not be the right thing to do. If these represent, like ages or blood pressures or weights or things that we're going to try to do some math on, like do some average values on, then we're just skewing our data, because obviously people can't have 0 ages and 0 weights. So filling something in with a simple value like 0 is probably not the right thing to do unless you're not going to try to average all the results together or something. Again, this is a mechanism, it's not a policy. You as a data scientist are still going to have to evaluate in every situation what's the appropriate thing to do, and you've got to think about the analytics in the process. What happens, do you think, if you say example 5.fillNA with an empty string? Again, not something you would do intentionally per se, but if you wanted to, you could deal with that way. So we had the question earlier about how do you deal with the missing strings. I'll still show you an answer to that in just a second, but just showing you that you can give it various values to fill in with, but also notice the impact is that converts the data frame back to an object data type, which means we can't do a lot of the precompiled math stuff. So that could have impacts on performance, particularly for large values. Well, if you don't want to fill in with 0, maybe you want to fill in with like the previous result. So let's say that you're taking temperature samples from an IoT device or something during the day, and for whatever reason you have some missing results. And let's say the day starts at 10 Celsius, and then it gets to 11, and then at its warmest it's up to maybe 14. In between 12 and 14, maybe we have a missing result. It would not be appropriate to set that to 0 because it didn't go 10, 11, 0, 14. And so that would obviously impact the data. But what we could say is just fill in the value from the previous value, right? So the forward fill does that for us. It takes the previous value and fills in for the missing value. So remember, our data is 1 non, 2 non, 3. So when I do a forward fill method, the 1 gets copied to the next one. Then we have a 2. Then the 2 gets copied to the next one. Then we have our 3. So forward fill fills in from the previous value. And that's often, like I said, that's often useful for time series data where things are climbing or falling, and it would be inappropriate to just remove a value and say, nope, let's set it down to 0. It's less impactful to just include it in the results that were there. Oftentimes you'll see that for stock prices and things where if you're looking at business days and you convert over to all days of the week, the previous stock price on Friday is still valid until Monday morning. So if you wanted to look at the stock price over the weekend, you would not have new results because those aren't reported over the weekend. So you could forward fill from Friday to the Monday, and over the weekend we'll just assume that the stock price remains the same. So that's the analytical reason why you might use forward fill. Occasionally you might want to backfill as well. So we have another method called bfill. And so notice we don't pull from the 2 to fill this non, we pull from the 3 to fill the non. We don't pull from the 1 to fill this non, we pull from the 2 to fill the non. So we're just filling backwards in this other direction. Now you can do that with data frames as well. So remember, we're dealing with series, and a data frame is really a collection of series for the columns. So obviously all the functions and everything still work. So if I do a forward fill on axis 1, that's going to be the column axis. Then we see this non is filled in from there. Now keep in mind, we're filling with respect to the columns. That's why we're specifying the axis. Even though it looks like we're dealing with the rows, we're filling in that direction. So 1 gets transferred over there, 7 gets transferred over there. And notice this ends up changing the data type with the types that's being set up. We've got a question, what if the first value is missing? Very good question. And we will see in just a moment that when you do a forward fill, the null value remains. right? So I'm not sure exactly why the won't work in Google Colab. I think they're mostly focused on working within VS Code. I don't know specifically what you might be running into, so I apologize about that. There may be some detail that VS Code is saving, but it's designed to work sort of more generally. All right, so if you have a missing value in a row or column and you forward fill or backfill in either way, it's left in place because you can't do anything with it. All right. So the question here is, what output does example 4 fill method bfill axis 1 produce? That's what I sorry, that's what I showed you up already. So if you don't specify axis 1, then it's going to forward fill with respect to the rows. And so notice the non in this position is filled in from the 2 there. The non here can't be forward filled from a previous version, which is what was just asked. So again, the axis tells us which direction we want to apply these things to as well. Another option for filling in the missing values is, let's say that I have sample of a population, and I keep track of things like height and weight. If I have a missing value for somebody, and I don't know what to put in there, but I do want to take the average of those values, then filling in the value with the missing value, or with the average value, isn't a reasonable approximation, right? It's not going to change the result like setting it to 0 would be. It may not be the right value for that particular thing, but if that's the average value, adding it in again and then dividing by the number of elements is not going to change the average value. So sometimes that's an appropriate thing to do. And we have a simple and easy, convenient way of doing that by simply saying fill in the missing value with the mean values. And so now we see our data set is 1, 2, and none. So the non is the missing value. So 1 plus 2 is 3 divided by 2. The average value of this column is 1.5 then, so we put that there. We have a non 5 and 6. So that's the missing value. 5 and 6 added together are 11 divided by 2 is 5.5. So you see how this keeps the data in roughly the same shape, roughly the same results. And analytically, that's probably going to be a more useful thing to do. One final approach to filling in values that you might consider is to maybe use the most common value. So for example, if you have some sales data and there's a category and the category has some missing values, you might fill it in and set it to be like, okay, if most people are buying food or music or books or something, filling in the most common value is sometimes a tool that data scientists use as well. So far we've identified where there are missing values. We've come up with ways of dropping them. We've come up with ways of filling them in. Those are all different approaches that can be useful in different scenarios prior to trying to do your analytics. Now, I think this is a very long workshop, so I don't think we're going to have time to go through it all. But hopefully, you've seen enough that you can continue to be successful. I will continue to go for a little bit longer, but there's a lot more to cover. So please do, if you're watching this on the video or following along at home, do continue to work through it because there's a lot of good utility here. And thank you, Sal, for the comment. All right. So what else might go wrong with the data? Well, particularly once you start merging things together, you may end up with duplicate data. Not necessarily a problem in and of itself, but if it represents actually the same observations multiple times or something like that, you do probably want to remove them because that might skew your data with respect to the distribution of values, right? It may look like a value shows up more often than it should. So sometimes when we have duplicates, we want to drop them. So let's generate some duplicates. We're going to create a data frame. We're going to have one column of letters and one column of numbers. And notice the fancy Python operator overloading here. So we're going to fill in A and B, and then A and B, and then a B. So we're just generating a list up there, and then we have 1, 2, 1, 3, 3. So we have 2 columns and our index. Now the question is, where do we have duplicates? Just like we have the is null and not null methods on the data frame and series, we also have duplicated. So notice the first row is not considered duplicated because we haven't seen an A and a 1 yet. A B and a 2 is not duplicated. At this point, A and 1 is now duplicated because we've seen one. B3, not duplicated. Next B3 is considered duplicated because we've seen one already. So this now is the index. We could use this like we use the other index to select the duplicated or not duplicated rows. But for the most part, we're just going to want to know if there are duplicates. So once we know that there are duplicates, we can then drop them. And now we have a data set that's every row is unique. Again, if you have duplicates, that's not necessarily a problem. Let's say that you are taking samples from some kind of IoT sensor, thermometer sensor or something, and it's 10C, and then the next one is 10C, and then the next one is 10C. That's not invalid, right? You have 3 samples. The temperature didn't change over those sample readings. So you're not always going to want to drop duplicated data, but if it's a question of merged results and a single observation is inappropriately replicated, that's going to be more likely the case where you will want to do so. Occasionally, you'll want to drop duplicates just with respect to a particular column. So I can give it the list of column names to drop the results. And so let me show you example 6 again, just so we see it here. So we don't want any duplication with respect to the letter column. So any row that's considered a duplicate from that perspective will get dropped. And we have the first 2, but that's like saying rather than using the compound key of the value in the first column and the volume in the second column, only use the value in the first column to do that. If I do a drop duplicates on numbers, we'll probably see something similar, except we'll have the 3 in there as well, right? So I can have duplicates in the letters, I just don't want duplicates on the number column. All right, so we have cleaned the data up, we've identified where there are missing values, we've come up ways of determining whether columns have missing values or rows have missing values. We've come up with ways of filling in the missing values, either setting them to 0 or to another value or to the mean value. We talked about setting the thresholds or the how for how we're dropping. That gives you some flexibility and nuance to the results. And then we looked at duplicates and possibly dropping duplicates as well. So we've covered quite a lot. I want to walk you through the rest of it. I'm not going to go through it all. I'm going to leave it for you, but just to highlight what's coming. The next thing that you want some assistance with is merging these data frames and joining them together. And just like if you've ever done any merge tables and inner and outer joins with SQL tables, you have the same capacity to do so here with Pandas. And this next section will walk you through that and get you comfortable with that. So you can do one-to-one joins, you can do many-to-one joins, you can do inner joins and outer joins, you can tell it which columns to join on, do left on, right on joins. So this is a very powerful way of merging data sets together. So if you're reading in from like a relational database and maybe you have a spreadsheet and you want to merge those data sets together, on various keys and columns, Pandas has great support for you for there. And then there are little tricks here and there about preserving the index or not preserving the index. So this will walk you through those. After you get comfortable with the merging and the joining, then the next section walks you through concatenation at the NumPy level. So if you have 3 arrays and you want to concatenate them together, that will generate an n-dimensional array. If you want to concatenate n-dimensional arrays together, that will give you the ability to sort of stack them in different forms, either on the row or column axes. So we'll see that. And then they connect it back to concatenation in Pandas. And then concatenation with joins, appends. So those are all different ways of merging these data structures together. It's a fun set of exercises. I encourage you to play around with it and see. But if you have a background at all in SQL table joins and whatnot, it'll look very, very familiar to you. And then the final section of this workshop is to tie it all together and to look at a particular data set. And so we're going to read in a data frame from an existing comma-separated variable data set. Notice the pd.readcsv. So this is reading in a comma-separated value file, turning it into a data frame. And this particular data frame is some historical data about the Boston housing market in the up until like the 70s. It's really depressing because they capped the expensive houses at $50,000. So that would buy you like a front door now in some places. But this exercise walks you through the experience of reading in this data set and then looking at the head and looking at the shape and seeing how much data is there and investigating the columns and looking at the values of the columns and finding the mean values of the prices and how do you interpret the results that you're seeing and how do the columns affect the value of the housing in those areas. So obviously things that are close to the work areas are nice. High pollution areas, the cost of the housing is probably lower because nobody wants to live there. So this final section is an applied data science using some of the tools that we've talked about with NumPy and Pandas, and ends with some nice visualizations, applying things. To answer the question about how to handle the missing values that are strings, one of the things you can do is to apply a lambda function, and this function will get applied to each of the strings, or each of the values of the columns. So you can check to see if something is an empty string and maybe fill it in with a default value, or otherwise, set it to an NA and then drop it or something. So hopefully that answers that question for you. So with this data set that you're reading in, the first goal is to do some exploration, get yourself familiar with it, and then it ends with a series of visualizations, and that's a lot of fun. So I hope this has been helpful. It's nice to want to be rock star machine learning data science people, but as I say in my classes, unlike most rock stars, these rock stars have to do a lot of sweeping and mopping, and this is what I mean by that. Any big comprehensive data set is going to have some issues that you're going to have to deal with and clean up, and if you don't do it, then any analysis that you do with that data is likely to be problematic and possibly misleading, right? Imagine filling in zeros for people's ages and then taking the average age. The net result would seem like, wow, people are on average a lot younger than I expected them to be. And it's not the kind of thing that's going to jump out at you right away. Like, wait a minute, why is this the case? That's why it's good to sort of catch yourself and do some checks to make sure that what you're seeing is what you expect to see. And that's one of the reasons why I like Jupyter Notebooks, right? Because you're telling stories, you're explaining what's going on, and if you need to stop and try something out, just add a cell and prove to yourself that things are what they seem to be. So thank you very much. Again, the video should be available if you want to go back and review things. The link has been shared for the repo. There's a ton of other workshop notebooks and stuff in there, and I encourage you to come back and join us again. Next week we'll be doing another session. Please also, we'll be sharing the survey link. It's important to keep track of what you find interesting and useful, and we hope that this has been helpful. Thank you very much. I appreciate that, and we hope to see you at a future session. So until then, please stay safe and enjoy playing around and doing some data science and machine learning.